3I-ATLAS is carrying enough carbon dioxide to jumpstart a dead planet's atmosphere, and it's heading straight for Mars with the timing of a Swiss atomic clock. Why is this interstellar visitor getting so close to the red planet just after NASA announced potential life signs in ancient Martian rocks? The timing is statistically impossible. The trajectory brings it within 30 million kilometers of Mars while hiding behind the Sun from Earth's telescopes. Tonight, we'll dissect this cosmic coincidence that has astronomers whispering and conspiracy theorists screaming, "This isn't random." In a universe governed by chaos and chance, nothing, absolutely nothing, should be this precise. Something is happening in Mars's orbital neighborhood that shatters our understanding of how the cosmos actually works. Stay with me, because what Atlas is really doing out there might be the most terrifying discovery in human history. There is life out there. NASA's Perseverance rover has been quietly digging through the ancient mudstones of Jezero Crater for over 4 years now. But in July 2024, something extraordinary emerged from the Martian soil. Scientists discovered what they're calling leopard spot textures embedded within a sample dubbed Shiava Falls collected near the Bright Angel outcrop. These aren't just pretty patterns in the rock. They represent one of the strongest potential biosignatures ever found on Mars. Let me translate what this actually means. A biosignature candidate is essentially nature's autograph, a chemical or physical trace that life might have left behind. The leopard spots contain minerals like vivianite and greigite compounds that, while they can form through purely geological processes, are also commonly produced by biological activity here on Earth. It's like finding footprints in ancient mud, except these footprints might have been made by microscopic Martian organisms 3.5 billion years ago. Jezero Crater wasn't always the barren, windswept basin we see today. Picture this: billions of years ago, this region hosted a sprawling lake fed by a meandering river system. The delta formations preserved in Jezero's geology tell the story of flowing water sediment deposition and organic chemistry, exactly the conditions where life tends to leave its calling cards. River deltas are nature's filing cabinets, preserving organic molecules and biological signatures in their layered sediments with remarkable fidelity. But here's where our story takes an unexpected turn. While scientists were announcing this potential evidence of ancient Martian life in September 2025, something else was happening in the darkness between the stars. On July 1st, 2025, the ATLAS telescope network detected an object unlike anything we'd seen before. They designated it 3I-ATLAS, making it only the third confirmed interstellar visitor in human history. ATLAS, the Asteroid Terrestrial Impact Last Alert System, operates like a celestial security guard scanning the entire sky every night from stations in Hawaii, Chile, and South Africa. These telescopes weren't built to find visitors from other star systems. They're designed to spot potentially hazardous asteroids that might threaten Earth. But sometimes, while searching for local threats, you stumble across something far more mysterious. 3I-ATLAS is traveling on what astronomers call a hyperbolic trajectory, a path that proves beyond doubt it originated from outside our solar system. Unlike the planets and comets born here which follow elliptical orbits bound to our sun, this object is essentially falling through our neighborhood on a one-way trip from the stars. Its orbital eccentricity exceeds one meaning. It carries enough speed to escape our sun's gravitational embrace forever. And here's what makes your pulse quicken while NASA announced Mars's strongest biosignature candidate. This interstellar wanderer was already racing toward a close encounter with the red planet itself. The timing seems almost purposeful. What we know about 3I-ATLAS reads like a cosmic mystery novel. It's confirmed to be natural, no artificial structures, no radio signals, no impossible maneuvers that would suggest intelligence. But its chemistry tells a different story. Early spectroscopic observations from the James Webb Space Telescope and SphereX reveal something unprecedented: a coma dominated by carbon dioxide with a CO2 to water ratio of approximately 8:1. Most comets are essentially dirty snowballs rich in water ice. This visitor seems to be breathing carbon dioxide into space. There are whispers in the astronomical community about a green glow observed in September, a phenomenon that could indicate dicarbon or cyanide compounds outgassing from the comet's nucleus. These aren't necessarily exotic chemicals, but their presence in such quantities in an object from another star system raises intriguing questions about where and how 3I-ATLAS formed. The internet predictably has exploded with theories alien artifact ancient probe design terraforming tool. NASA's response has been measured and scientific. All current observations are consistent with a natural comet, albeit one with unusual composition. There's no threat to Earth, no evidence of artificial origin, and no reason to panic. But that's not what keeps me staring at the data late into the night. It's the timing. It's the chemistry. It's the way this story seems to be writing itself across the cosmos. If someone or something wanted to nudge Mars toward habitability, what would be the perfect delivery mechanism? A comet rich in greenhouse gases, perhaps carbon dioxide, that could thicken Mars's anemic atmosphere, trap solar heat, and begin the long process of planetary resurrection. Of course, this is speculation wrapped in cosmic coincidence, but as we'll explore in the coming minutes, sometimes the universe presents us with patterns so compelling, so elegantly structured, that dismissing them outright feels almost unscientific. What is 3I-ATLAS doing in Mars's orbit? That question will guide us through a labyrinth of astronomy, ancient mysteries, and the possibility that we're witnessing something far more significant than a simple cosmic coincidence. Buckle in. We're about to take a journey that begins with chemistry and ends with questions that might reshape how we think about life intelligence and our place in an infinite cosmos. To understand why 3I-ATLAS is so extraordinary, we need to grasp what makes an orbit hyperbolic. Imagine throwing a ball straight up into the air. It follows a parabolic arc, slowing down, stopping, then falling back to Earth. Now imagine throwing that ball so hard it never comes back down, escaping Earth's gravity entirely. That's essentially what a hyperbolic orbit represents on a cosmic scale. When astronomers measure an orbit's eccentricity, they're calculating how stretched or circular it is. Perfect circles have an eccentricity of 0. Earth's slightly oval orbit has an eccentricity of about 0.017. But when eccentricity exceeds 1, you're dealing with an escape trajectory, a path that carries an object away from its gravitational host forever. 3I-ATLAS has an eccentricity well above 1, proving conclusively that it originated from interstellar space. This makes it only the third confirmed visitor from beyond our solar system, joining the enigmatic cigar-shaped 1I-ʻOumuamua in 2017 and the more conventional comet 2I Borisov in 2019. But here's where things get interesting. Oumuamua exhibited mysterious non-gravitational acceleration. It sped up in ways that couldn't be explained by solar radiation pressure alone, leading to wild speculation about artificial origin. Borisov, by contrast, behaved exactly like the comets we're familiar with, complete with the typical dust and gas coma and predictable outgassing patterns. 3I-ATLAS falls somewhere between these extremes, and that's what makes it fascinating. It's clearly natural. No geometric shapes, no radio transmissions, no impossible physics. But its chemical signature reads like something from an alien chemistry textbook. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has been studying 3I-ATLAS since its discovery. What it found defies expectations. A coma, that fuzzy envelope of gas and dust surrounding the nucleus, dominated not by water vapor as we'd expect, but by carbon dioxide. The CO2 to H2O ratio measures approximately 8:1 among the highest ever recorded for any comet. To put this in perspective, most comets are like cosmic snowballs. As they approach the sun, solar heating sublimates their icy surfaces, creating the familiar tale of water vapor dust and trace gases. The dirty snowball model has served us well for decades, but 3I-ATLAS seems to be exhaling carbon dioxide the way a frozen block of dry ice steams in warm air. This unusual chemistry suggests several possibilities. Perhaps 3I-ATLAS formed near the carbon dioxide ice line in its original stellar system, where temperatures were just right for CO2 to freeze solid while water remained gaseous. Maybe its surface has been processed by cosmic radiation during millions of years in interstellar space, creating a carbon-rich crust that preferentially releases CO2 when heated. There's another intriguing possibility: selective sublimation. If the comet's nucleus is coated with a layer of carbon dioxide ice, this could suppress the release of deeper water ice reservoirs, skewing the observed ratios towards CO2 dominance. As 3I-ATLAS continues its journey toward the Sun, we might see this ratio evolve, revealing different layers of its frozen history. Recent observations have detected additional compounds, carbon monoxide, carbonyl sulfide, and water ice, buried beneath the carbon dioxide-rich surface. Each detection adds another piece to the puzzle of this visitor's origin story. The Sphere-X Space Telescope, with its specialized infrared capabilities, has confirmed these measurements, independently lending credibility to what initially seemed like impossible chemistry. Then there's the green glow. In September, ground-based observers reported a distinct emerald tint to 3I-ATLAS's coma. This coloration typically indicates the presence of dicarbon molecules, two carbon atoms bonded together, or possibly cyanide compounds. While neither substance is particularly exotic in cometary terms, their abundance in an interstellar visitor raises questions about the chemical processes at work in distant stellar nurseries. The viral speculation about alien artifacts has prompted measured responses from NASA and ESA scientists. Dr. Alan Fitzsimmons from Queen's University Belfast, who has extensive experience studying interstellar objects, noted that while 3I-ATLAS's composition is unusual, all observations remain consistent with natural phenomena. No structured radio signals, no geometric perfection, no impossible accelerations, just chemistry that challenges our assumptions about comet formation. But here's what keeps astronomers awake at night: the measurement limitations. Early spectroscopic observations can be contaminated by dust-atmospheric interference and the object's rapidly changing distance from both the Sun and Earth. Chemical ratios can evolve dramatically as solar heating penetrates deeper into a comet's nucleus, potentially revealing entirely different compositions as the mission progresses. We're essentially trying to analyze a chemistry set traveling at 30 kilometers per second, millions of miles away, through a telescope. The fact that we can detect anything meaningful is remarkable. The fact that what we're detecting challenges our understanding of interstellar chemistry is unsettling. As 3I-ATLAS races toward its rendezvous with Mars, these chemical anomalies take on new significance. Carbon dioxide isn't just an unusual cometary component. It's the primary constituent of Mars's atmosphere, the key greenhouse gas that once gave the red planet a thicker, potentially life-supporting environment. If someone wanted to nudge Mars back toward habitability, carbon dioxide would be the perfect delivery mechanism. But we're getting ahead of ourselves. Right now, we're dealing with chemistry that's unusual, but not impossible timing. That's coincidental, but not supernatural, and a trajectory that's bringing this cosmic chemistry set within 30 million kilometers of Mars in just a few weeks. The question that haunts every observation, every spectrum, every carefully calibrated measurement is simple. Why now? Why this chemistry? And why Mars? Mark your calendars for October 3rd, 2025. On that date, 3I-ATLAS will sweep past Mars at a distance of approximately 28 to 30 million kilometers, roughly 0.19 to 0.20 astronomical units for those keeping score. To put this in perspective, that's about 75 times farther than the Moon is from Earth. Close in cosmic terms, but not exactly a near miss. But here's where the story gets cinematically perfect. Just as 3I-ATLAS makes its closest approach to Mars, it will be effectively invisible from Earth. The reason is solar conjunction. The object will be positioned behind the Sun, from our perspective hidden in the solar glare like a whisper drowned out by a symphony. For several crucial weeks in late September through late October, Earth-based telescopes will be essentially blind to whatever 3I-ATLAS might be doing near Mars. The timing feels almost orchestrated. Maximum proximity to Mars coincides with maximum invisibility from Earth. If you were writing a science fiction thriller, you couldn't ask for better dramatic tension. 3I-ATLAS will reach perihelion, its closest approach to the Sun, on October 29th or 30th, positioning it just inside Mars's orbit at approximately 1.4 astronomical units from our star. This places the comet in the perfect sweet spot for solar heating to maximize outgassing while maintaining that tantalizing proximity to the red planet. But we won't be completely blind to this cosmic encounter. The European Space Agency has confirmed that Mars orbiters are preparing to attempt observations during the October flyby. Mars Express operational since 2003, and the Trace Gas Orbiter, which has been studying Martian atmospheric chemistry since 2016, represent our best chance of getting close-up data on 3I-ATLAS during its Mars passage. What could these orbiters potentially observe? The possibilities are tantalizing. High-resolution imaging might reveal details of the comet's nucleus and coma structure invisible from Earth. Ultraviolet and infrared spectrometers could detect specific emission lines from cyanide carbon monoxide and other trace compounds. Dust analyzers might even capture particles from the comet's tail, providing direct samples of interstellar material. The scientific stakes couldn't be higher. 3I-ATLAS represents our third data point for understanding interstellar chemistry and potentially our best opportunity to compare the volatile compounds that form around other stars with those native to our own solar system. The unusually high carbon dioxide content could provide insights into planet formation processes in distant stellar nurseries. But there's another layer to consider. Mars itself is undergoing renewed scientific scrutiny following the potential biosignature discoveries in Jezero Crater. The red planet's thin atmosphere, composed of 95% carbon dioxide, represents the remnant of what was once a thicker, more Earth-like envelope. Billions of years ago, Mars likely had enough atmospheric pressure to support liquid water on its surface, the lakes and rivers that carved Jezero Crater, and countless other features across the planet. What if we're witnessing more than just a cosmic coincidence? What if the carbon dioxide-rich chemistry of 3I-ATLAS represents exactly the kind of atmospheric replenishment Mars would need to reverse its climate catastrophe? Of course, we need to maintain perspective on the scales involved. A single comet, even one with unusual volatile content, carries nowhere near enough gas to meaningfully alter a planetary atmosphere. Mars has been losing its atmosphere to space for billions of years, stripped away by solar wind due to the planet's lack of a strong magnetic field. One comet's worth of carbon dioxide would be like adding a cup of water to an empty swimming pool. But what if 3I-ATLAS isn't alone? What if we're observing just one delivery in a long-term process of atmospheric restoration? The reassuring news is that 3I-ATLAS poses no threat to Earth. Its closest approach to our planet won't occur until mid-December, when it will pass at a comfortable distance of approximately 1.8 astronomical units, about 168 million kilometers away. That's farther than the Sun, making it safer than our daily dose of solar radiation. Still, the geometry is remarkable. An interstellar visitor loaded with the exact atmospheric components Mars needs most arriving, just as we discover the strongest evidence yet for ancient Martian life. The comet will be hidden from Earth observation during its Mars encounter, creating a perfect window of cosmic privacy. If this were a movie script, editors would reject it as too coincidental to be believable. Ground-based observations will resume once 3I-ATLAS emerges from behind the Sun in late November and December. By then, post-perihelion heating will have fundamentally altered the comet's chemistry and appearance. We might be looking at a completely different object, one that's shed its outer layers and revealed whatever secrets lie frozen in its core. The European Space Agency has been remarkably transparent about the observational challenges ahead. Unlike previous interstellar visitors, 3I-ATLAS's trajectory and timing make it impossible to launch an intercept mission. The speeds and distances involved are simply beyond our current technological capabilities. We're limited to remote observation, spectroscopic analysis, and whatever data the Mars orbiters can collect during those precious few days in October. But perhaps that's fitting. Sometimes the most profound mysteries can only be observed, not touched. Sometimes the questions matter more than the answers. As 3I-ATLAS races toward its appointment with Mars carrying its cargo of carbon dioxide and cosmic secrets, we're left to wonder what exactly will happen during those invisible weeks behind the Sun. What will the Mars orbiters see? And what story will 3I-ATLAS tell us about the chemistry of distant stars and possibly the future of our neighboring planet? The orbital mechanics are clear, the chemistry is puzzling, the timing is uncanny, and in just a few weeks, an object from the stars will sweep past Mars while Earth looks the other way, leaving us to piece together the story from whatever clues remain in its wake. Let's state the coincidence clearly without embellishment. In September 2025, NASA announced the discovery of potential biosignatures in Martian rocks' leopard spot textures that might represent the strongest evidence yet for ancient life on Mars. Weeks later, 3I-ATLAS, an interstellar comet rich in carbon dioxide, will make its closest approach to the red planet before disappearing behind the sun for crucial weeks of invisible proximity. Correlation, as any scientist will tell you, does not imply causation. But in a universe where timing often seems meaningful, where patterns emerge from apparent chaos, such coincidences demand examination, if only to understand why our pattern-seeking minds find them so compelling. The rational explanation is straightforward. Interstellar objects arrive from random directions at random times following the inexorable laws of celestial mechanics. 3I-ATLAS began its journey from some distant stellar neighborhood millions of years ago, long before humans existed, let alone developed the capability to detect biosignatures on Mars. Its hyperbolic trajectory was set by the gravitational dynamics of its birth system, modified by countless stellar encounters during its lonely voyage through the cosmic void. Hyperbolic orbits don't lie. When we calculate an eccentricity greater than 1, we're measuring something fundamental about an object's history and destiny. 3I-ATLAS is unbound to our sun, carrying excess velocity that will eventually carry it back into interstellar space. This isn't a captured object that somehow got aimed at Mars. It's a visitor on a one-way trip following laws of physics that care nothing about human discovery timelines or planetary biology. But here's where the story gets interesting. From a purely narrative perspective in conspiracy theories and thriller plots, coincidences don't exist in isolation. They pile up layer upon layer until the accumulated weight of circumstantial evidence becomes impossible to ignore. So let's examine what we're actually dealing with. First, there's the perihelion geometry. 3I-ATLAS will reach its closest approach to the Sun on October 29th or 30th, positioning it just inside Mars's orbit at a distance of approximately 1.4 astronomical units. This places the comet in the optimal zone for maximum solar heating and outgassing exactly when it's nearest to Mars and furthest from Earth's prying telescopes. The timing of solar conjunction when 3I-ATLAS disappears behind the Sun from Earth's perspective creates a perfect window of observational blindness. For several crucial weeks, our most powerful telescopes will be unable to monitor what's happening near Mars. If someone wanted to conduct cosmic business in private, they couldn't ask for better cover. Then there's the chemistry that keeps nagging at researchers. Carbon dioxide dominance in a comet is unusual, but not impossible. However, CO2 happens to be precisely what Mars needs most for atmospheric restoration. The red planet's current atmosphere is already 95% carbon dioxide, but it's desperately thin, less than 1% of Earth's atmospheric pressure. Any process that could add greenhouse gases might help reverse the atmospheric loss that turned Mars from a potentially habitable world into the frozen desert we see today. The public confusion about interstellar versus interplanetary missions reflects a deeper misunderstanding about the nature of cosmic visitors. 3I-ATLAS isn't a spacecraft that can be steered or redirected. It's following a trajectory determined by fundamental physics influenced only by the gravitational fields it encounters. No course corrections, no intelligent guidance, no signs of artificial propulsion, just a chunk of frozen chemistry obeying Newton's laws. NASA's position has been consistently clear. All observations of 3I-ATLAS are consistent with natural comet behavior. No structured signals, no geometric perfection, no impossible maneuvers that would suggest intelligence. The object poses no threat to Earth and shows no signs of artificial origin. So why does the timing feel so significant? Perhaps because we're witnessing the intersection of two separate cosmic narratives that our minds insist on connecting. Ancient life on Mars represents a story about the past biology that might have flourished when the red planet had a thicker atmosphere and flowing water. 3I-ATLAS represents a story about the present interstellar chemistry arriving at precisely the moment we're contemplating Mars's biological potential. But here's a thought experiment that pushes the envelope of speculation. What if atmospheric engineering isn't science fiction? What if the chemistry we're observing in 3I-ATLAS, carbon dioxide rich, arriving at Mars with perfect timing, represents not coincidence, but design? Not alien design necessarily, not little green men piloting cosmic snowballs, but design in the sense of natural selection operating on cosmic scales. What if the universe tends to produce interstellar objects with chemistry that promotes planetary habitability? What if the same processes that create life-supporting atmospheres also generate the delivery mechanisms to maintain them? This ventures well into speculative territory, but it's worth noting that carbon dioxide and water, the primary components we've detected in 3I-ATLAS, are also the fundamental building blocks of planetary atmospheres capable of supporting life as we know it. The ratio might be unusual, but the chemistry is precisely what any terraforming project would prioritize. Of course, this assumes that terraforming is even possible on Mars, which remains highly speculative. The red planet lacks a strong magnetic field to protect its atmosphere from solar wind erosion. Even if 3I-ATLAS deposited its entire mass of volatiles into Mars's atmosphere, the long-term loss mechanisms would eventually strip away any temporary gains. But what if we're thinking too small? What if 3I-ATLAS isn't a single event, but part of a larger pattern? The third confirmed interstellar visitor in less than a decade suggests these objects might be more common than previously thought. As our detection capabilities improve, we might discover that interstellar chemistry delivery is a regular feature of cosmic evolution. This leads us to two possible tracks for understanding what we're witnessing. The sober scientific track treats 3I-ATLAS as an unusual but natural comet whose timing near Mars is purely coincidental. The data supports this interpretation. The physics makes sense, and no extraordinary claims require extraordinary evidence. The speculative track asks different questions. Why this chemistry? Why this timing? Why Mars? It doesn't necessarily invoke intelligence or design, but it remains open to patterns and possibilities that might not fit conventional frameworks. Both tracks acknowledge the same fundamental mystery. We're living through a moment when ancient Martian biology and interstellar chemistry are converging in ways that challenge our assumptions about cosmic coincidence. If someone wanted to terraform Mars, what would they deliver? Carbon dioxide for greenhouse warming water, for biological processes, organic compounds for chemical complexity. The exact cocktail we're observing in 3I-ATLAS's coma. The question that bridges both scientific rigor and speculative wonder is this: how do we distinguish between meaningful patterns and mere coincidence in a universe that seems equally capable of both? The gaps in our knowledge about 3I-ATLAS create perfect breeding grounds for extraordinary theories, limited visibility during its crucial Mars encounter, evolving spectroscopic data as the comet heats up, and the inherent challenges of analyzing chemistry at interstellar distances. Each uncertainty becomes fertile soil for speculation to take root. Consider what we're actually dealing with from an observational standpoint. 3I-ATLAS was discovered on July 1, 2025, giving us less than 4 months to study it before solar conjunction renders it invisible from Earth. That's barely enough time to establish basic orbital parameters, let alone conduct detailed compositional analysis of an object traveling at 30 kilometers per second through the vacuum of space. The online debate reflects this uncertainty in predictable ways. Social media algorithms reward extreme interpretations, amplifying claims about alien artifacts and cosmic conspiracies, while burying measured scientific analysis in feeds optimized for engagement rather than accuracy. High-profile figures with millions of followers can shape public perception of 3I-ATLAS with a single inflammatory post, regardless of their actual expertise in astronomy or astrobiology. NASA's response has been textbook crisis communication: acknowledge the unusual observations, explain the natural phenomena that could account for them, and emphasize that no evidence supports artificial origin or Earth-threatening behavior. Dr. Paul Chodas from the Center for Near-Earth Object Studies has been particularly clear. All current data are consistent with 3I-ATLAS being a natural comet with unusual but not impossible chemistry. But here's what makes this situation different from previous false alarms. The detection networks that found 3I-ATLAS are specifically designed to be transparent and rapid. The ATLAS telescope system publishes observations within hours of detection, making it virtually impossible to suppress or hide data about potentially hazardous objects. If 3I-ATLAS were behaving in truly anomalous ways, making course corrections, emitting structured signals, or exhibiting geometric perfection, the evidence would be immediately available to astronomers worldwide. This transparency is both reassuring and slightly disappointing. The romantic notion of government cover-ups and hidden cosmic visitors crashes against the reality of modern astronomy, a global network of observers, automated detection systems, and international cooperation that makes astronomical secrets nearly impossible to maintain. The physics of interplanetary travel also constrains the more exotic theories about 3I-ATLAS. Its hyperbolic trajectory and current distance from Earth make it impossible to launch an intercept mission with existing technology. The European Space Agency has been explicit about this limitation. We simply don't have spacecraft capable of matching the object's velocity and trajectory on such short notice. This inability to directly sample 3I-ATLAS means we're limited to remote observation spectroscopic analysis and whatever data the Mars orbiters might collect during the October encounter. It's like trying to identify a person's nationality, profession, and intentions by watching them walk past your window at night from several blocks away. Yet the very limitations of our observational capabilities create space for both healthy scientific skepticism and unhealthy conspiracy thinking. What exactly would constitute proof that 3I-ATLAS is artificially engineered? The criteria are actually quite specific, non-Keplerian orbital maneuvers that suggest propulsion, narrowband radio transmissions, indicating intelligence geometric structures visible in high-resolution imaging, or chemical signatures that couldn't occur naturally. None of these have been observed. 3I-ATLAS follows a perfectly predictable hyperbolic trajectory consistent with gravitational physics. No radio telescopes have detected artificial signals. Its coma appears fuzzy and diffuse, lacking the sharp edges or geometric patterns that would suggest manufactured origin. Even its unusual chemistry, while puzzling, falls within the range of what's theoretically possible for comets formed in different stellar environments. But the absence of evidence isn't always evidence of absence, as the saying goes. The real question is whether we're looking hard enough with the right instruments at the right times for the right signatures. The green glow reported in September adds another layer of intrigue and uncertainty. Dicarbon and cyanide compounds can indeed produce emerald coloration in cometary comas, but the exact molecular processes responsible for the observed tint remain unconfirmed. Different telescopes, different atmospheric conditions, and different observational techniques can yield conflicting results about color and composition. This is where the noir elements of our story become most apparent. Science corrects, but conspiracy connects. Scientific methodology requires multiple independent confirmations, peer review, and statistical significance before accepting extraordinary claims. Conspiracy thinking, by contrast, weaves isolated observations into compelling narratives that resist conventional verification. 3I-ATLAS exists in the liminal space between these two approaches. Its unusual chemistry is scientifically interesting, but not impossible. Its timing near Mars is cosmically coincidental, but not supernatural. Its period of invisible proximity to the red planet is astronomically normal, but dramatically perfect. The object seems designed to frustrate both conventional explanation and extraordinary interpretation. Too weird to be completely ordinary, too ordinary to be completely weird. This ambiguity creates what psychologists call the uncertainty effect. Our minds become more active, more pattern-seeking, more willing to entertain unusual possibilities when confronted with incomplete information. 3I-ATLAS provides just enough anomalous data to trigger our curiosity while remaining just within the bounds of natural phenomena. As we prepare to lose visual contact with the comet during its Mars encounter, we're forced to confront the limitations of human knowledge and the power of cosmic timing. For several weeks, 3I-ATLAS will be doing something near Mars, while Earth's telescopes point uselessly at empty sky. When we regain contact in late November, will we be looking at the same object? Solar heating during perihelion passage can fundamentally alter a comet's appearance, stripping away surface layers and revealing entirely different chemical compositions. The 3I-ATLAS that emerges from behind the Sun might tell a completely different story than the one that disappeared in October. This evolution adds yet another variable to our growing collection of uncertainties. Are we studying one object or two? Is the chemistry we've measured representative of the entire nucleus or just its outermost layers? Will the post-perihelion 3I-ATLAS confirm our natural comet hypothesis or reveal something that challenges our understanding of interstellar chemistry? The most unsettling possibility is that we might never know for certain. 3I-ATLAS could complete its Mars encounter, undergo perihelion heating, and depart our solar system carrying its secrets back to the interstellar void. We'd be left with spectroscopic data, orbital calculations, and endless speculation about what really happened during those invisible weeks in October. Perhaps that's the real test. Not whether 3I-ATLAS is natural or artificial, but whether we can maintain scientific rigor while acknowledging the profound mystery of our cosmic circumstances. Can we hold two seemingly contradictory ideas simultaneously, that the universe is stranger than we imagine, and that extraordinary claims require extraordinary evidence? What if the most important question isn't what 3I-ATLAS is, but what its arrival reveals about our readiness to encounter truly anomalous phenomena? What if this is less about chemistry and more about consciousness, a test of our ability to think clearly in the presence of cosmic ambiguity? What if the real mystery isn't what 3I-ATLAS is doing in Mars's orbit, but what we're supposed to learn from watching it happen? Long before NASA telescopes scanned the cosmos for interstellar visitors, human beings watched the skies with a mixture of wonder and terror. Ancient astronomers, Sumerian, Egyptian, Mayan, Chinese, developed sophisticated systems for tracking celestial motion, but they had no framework for understanding objects that might originate beyond our solar system. The historical record contains no verified accounts of 3I-ATLAS-like visitors, but this absence might tell us more about observational limitations than cosmic reality. Ancient sky watchers focused on regular, predictable phenomena, the movements of planets, the cycles of eclipses, the seasonal appearance of familiar constellations. A faint, fast-moving object on a hyperbolic trajectory would likely appear as little more than a dim star that wandered across the heavens for a few weeks before vanishing forever. Yet mythology is filled with stories that could, with considerable imagination, be interpreted as garbled memories of unusual astronomical events. Skyboats carrying gods between worlds, celestial messengers arriving during times of great change, wandering stars that appeared without warning and disappeared just as mysteriously. The Sumerian creation epic ʻOumuamua describes Marduk arriving from the outer darkness to battle primordial chaos and establish cosmic order. Egyptian mythology speaks of solar barges that carried divine consciousness across the celestial ocean. Mayan astronomers tracked Venus with extraordinary precision, but also recorded guest stars that modern researchers interpret as supernova or comets. These parallels are fascinating as cultural artifacts, but we must be crystal clear there's no evidence linking ancient mythology to modern interstellar objects. The human tendency to find patterns in coincidence operates as powerfully now as it did 4,000 years ago. When we encounter something truly unusual like 3I-ATLAS, we instinctively search for historical precedents even when none exist. This pattern-seeking behavior served our ancestors well when distinguishing between rustling bushes that contained predators versus those that contained only wind. But when applied to cosmic phenomena, the same cognitive tools that once ensured survival can lead us down rabbit holes of confirmation bias and false correlation. Consider how comets historically functioned as omens of political and social change. The appearance of Halley's Comet in 1066 was interpreted as predicting the Norman conquest of England. The Great Comet of 1577 convinced European nobles that God was announcing the Protestant Reformation. Chinese astronomers developed elaborate systems for correlating celestial visitors with dynastic transitions. None of these correlations proved causal, of course. Comets don't influence human politics any more than human politics influence cometary orbits. But the psychological power of cosmic timing created feedback loops where unusual astronomical events became self-fulfilling prophecies shaping human behavior in ways that made the predictions appear accurate. 3I-ATLAS arrives during a similar moment of historical transition. Human civilization stands at a crossroads between planetary and interplanetary existence. We've discovered potential biosignatures on Mars, developed the technology to deflect asteroids, and begun serious planning for permanent settlements beyond Earth. The comet's arrival coincides not just with Mars' discoveries, but with humanity's emergence as a spacefaring species. Is this timing meaningful, or are we simply more sensitive to cosmic events because we've finally developed the tools to detect and analyze them? The anthropic principle suggests that we observe the universe at precisely the moment when observation becomes possible, not because the universe was waiting for us, but because we couldn't have observed it any earlier. Yet there's something deeply unsettling about the precision of these coincidences. 3I-ATLAS doesn't just arrive during a period of Mars exploration. It arrives specifically as we discover the strongest biosignature evidence in Jezero crater. It doesn't just pass through the inner solar system, it approaches Mars at exactly the distance and timing that would maximize scientific intrigue while minimizing observational certainty. Ancient cultures dealt with this type of cosmic synchronicity by invoking divine intervention or supernatural design. Modern cultures struggle to find equivalent explanatory frameworks that satisfy both our scientific skepticism and our intuitive sense that some patterns transcend mere coincidence. The classical planet Mars, named for the Roman god of war, carries cultural baggage that influences how we interpret events in its vicinity. The red planet has always represented conflict, change, and transformation in human consciousness. When an interstellar visitor approaches Mars, our mythological programming activates whether we acknowledge it or not. But perhaps the most intriguing historical parallel isn't found in ancient texts. It's found in the evolution of human observation itself. Each generation develops new tools for seeing the cosmos, and each new tool reveals phenomena that previous generations couldn't detect or understand. Radio telescopes revealed pulsars. Space-based observatories discovered exoplanets. The ATLAS network now detects interstellar visitors. What if the pattern isn't that unusual objects arrive at meaningful moments, but that our definition of meaningful expands to accommodate whatever we're capable of observing? What if 3I-ATLAS has been making similar approaches to Mars for millions of years, but only now do we have the technology to detect its chemistry and the cultural context to find its timing significant? This raises a provocative question. If advanced civilizations wanted to leave breadcrumbs for developing species, where would they hide them? The answer might be in plain sight, but coded in phenomena that become visible only when a species reaches sufficient technological and intellectual maturity to decode them. Such breadcrumbs wouldn't need to be artificial artifacts. They could be natural phenomena, arranged or timed in ways that convey information to sufficiently advanced observers. A comet with unusual chemistry arriving during a moment of astrobiological discovery. Spectroscopic signatures that reveal themselves only to civilizations capable of infrared astronomy. Orbital mechanics that create meaningful coincidences for species sophisticated enough to calculate hyperbolic trajectories. Of course, this ventures well into speculative territory. We have no evidence that 3I-ATLAS represents anything more than natural chemistry following natural laws. But the framework of natural breadcrumbs provides a useful thought experiment for understanding why certain cosmic events feel pregnant with meaning, even when conventional analysis suggests pure coincidence. Our methodology moving forward must be explicitly bifurcated. We'll entertain possibilities while rigorously checking them against available data. We'll explore patterns while acknowledging the human tendency to impose meaning on random events. We'll ask what-if questions while maintaining what-is standards of evidence. The ancient astronomers who tracked planetary motions and recorded celestial events were doing something profoundly important, even when their interpretations were wildly incorrect. They were establishing the observational foundation that would eventually enable us to detect 3I-ATLAS and calculate its interstellar origin. Their pattern-seeking meaning-making impulses, however misguided, were practice runs for the pattern-seeking we're doing now. The difference is that we have better tools and stricter methodologies, but the fundamental human response to cosmic mystery remains unchanged. We watch, we wonder, and we try to understand our place in an apparently infinite universe that occasionally presents us with phenomena that seem almost too coincidental to be truly coincidental. What if the sky gods our ancestors imagined were simply their way of describing realities they could sense but not yet measure? What if 3I-ATLAS is exactly the kind of phenomenon that would have inspired myths about celestial messengers if only ancient observers had possessed telescopes powerful enough to detect it? Every few years, internet culture rediscovers the supposed 3,600-year cycle of Nibiru, a mythical planet that allegedly approaches Earth on a highly elliptical orbit, bringing with it ancient astronauts, genetic manipulation, and the rise and fall of human civilizations. The story originates primarily with Zecharia Sitchin, whose translations of Sumerian cuneiform tablets propose that advanced beings called the Anunnaki visited Earth periodically to mine gold and interfere with human evolution. NASA has spent considerable resources debunking these claims. There is no rogue planet on a collision course with Earth. No gravitational evidence suggests a massive body lurking in the outer solar system on a 3,600-year orbit. No astronomical observations support the existence of Nibiru despite decades of sophisticated sky surveys that would easily detect such an object. The Nibiru mythology represents exactly the kind of pseudo-scientific thinking that makes genuine astronomical anomalies like 3I-ATLAS so difficult to discuss rationally. When the internet is flooded with claims about ancient astronauts and planetary conspiracies, legitimate scientific mysteries get lost in the noise of unfalsifiable speculation. But here's what makes 3I-ATLAS fundamentally different from Nibiru fantasies. It's real, it's observed, and its behavior follows predictable laws of physics. Multiple observatories have tracked its trajectory independently. Its hyperbolic orbit has been calculated and verified. Its chemistry has been analyzed by the most sophisticated instruments humanity has ever built. 3I-ATLAS doesn't return every 3,600 years because it's not bound to our solar system. Hyperbolic orbits are one-way tickets. Objects that follow them arrive from interstellar space and depart to interstellar space, never to return. This is mathematics, not mythology. Yet the persistent appeal of cyclical cosmic events reveals something important about human psychology. We find comfort in patterns, even fictional ones. The idea that significant events repeat on predictable schedules gives us a sense of control over forces that are otherwise incomprehensible. If we can predict when the gods return, maybe we can prepare for their arrival. Real interstellar objects like 3I-ATLAS offer no such comfort. They arrive without warning from random directions, follow trajectories determined by physics rather than prophecy, and depart forever into the cosmic void. There's no cycle to decode, no pattern to predict, no way to prepare for the next encounter because we have no idea when or if it will occur. This unpredictability might be more unsettling than the cold certainty of mythical cycles. At least Nibiru enthusiasts know what they're expecting and when to expect it. 3I-ATLAS offers only questions. Where did it come from? Why does its chemistry seem so perfectly suited for Mars' atmospheric restoration? What will happen during its invisible encounter with the red planet? The contrast between science-based uncertainty and unfalsifiable mythology illustrates why critical thinking is so crucial when evaluating cosmic anomalies. Science admits ignorance, proposes testable hypotheses, and updates conclusions based on new evidence. Pseudoscience claims certainty, resists testing, and interprets all evidence as confirmation of predetermined beliefs. But we shouldn't dismiss the psychological needs that drive people towards cyclical cosmic narratives. The universe really is vast, ancient, and filled with phenomena that dwarf human comprehension. The desire to find meaningful patterns in cosmic chaos represents a deeply human response to existential uncertainty. What if we could harness that pattern-seeking impulse in service of legitimate scientific inquiry instead of imposing fictional cycles on random events? What if we looked for genuine patterns in the limited data we have about interstellar visitors? 3 confirmed interstellar objects in less than a decade suggest these visitors might be more common than previously thought. 1I-ʻOumuamua exhibited unusual acceleration. 2I Borisov behaved like a conventional comet. 3I-ATLAS shows unusual chemistry and uncanny timing. That's hardly enough data for statistical analysis, but it's enough to suggest that interstellar space might be more chemically diverse than our models predict. The real 3,600-year cycle isn't the return of ancient astronauts. It's approximately how long human civilization has maintained written records sophisticated enough to detect patterns in cosmic events. We've been watching the skies systematically for roughly that long, developing increasingly powerful tools for observation and analysis. What if the meaningful cycle isn't cosmic, but technological? Every few generations, we develop new capabilities for detecting and analyzing celestial phenomena. Each technological leap reveals new classes of objects and events that were always there but previously invisible. Radio telescopes revealed pulsars, quasars, and the cosmic microwave background. Space-based observatories detected gamma-ray bursts, gravitational waves, and thousands of exoplanets. Automated sky surveys now detect asteroids, supernovae, and interstellar visitors with unprecedented precision. 3I-ATLAS represents the latest iteration of this technological evolution. We can now detect, track, and analyze the chemistry of objects from other star systems. This capability is less than a decade old, which means we're still learning what's normal versus anomalous for interstellar visitors. The internet amplifies both the benefits and dangers of this rapid technological progress. Legitimate astronomical discoveries spread globally within hours, enabling unprecedented collaboration and verification. But misinformation spreads just as quickly, mixing genuine scientific mysteries with ancient astronaut theories and conspiracy speculation. The challenge is maintaining scientific rigor while acknowledging that our current understanding of interstellar chemistry and orbital mechanics might be incomplete. 3I-ATLAS doesn't fit neatly into existing categories, but that doesn't mean it requires extraordinary explanations. Sometimes nature is simply more creative than our models anticipate. Could ancient myths represent distorted memories of real astronomical events? Possibly. Bright comets, meteor showers, and aurora displays would have seemed supernatural to pre-industrial observers. But there's a crucial difference between acknowledging that astronomy influences mythology and claiming that mythology accurately describes astronomy. The Sumerian tablets that Sitchin translated contain remarkable achievements in mathematics, astronomy, and engineering. But they reflect the cosmological understanding of their time, not secret knowledge delivered by extraterrestrial visitors. When we project modern scientific concepts onto ancient texts, we usually learn more about our own assumptions than about historical realities. 3I-ATLAS offers us an opportunity to practice better intellectual hygiene. We can acknowledge its unusual properties without invoking ancient astronaut theories. We can explore its implications for Mars' atmospheric chemistry without claiming it represents deliberate terraforming. We can ask profound questions about cosmic timing and interstellar delivery mechanisms without abandoning the standards of evidence that distinguish science from speculation. The real cycle worth understanding isn't the mythical return of Nibiru. It's the recurring human tendency to find meaning in cosmic events and our evolving capacity to test those meanings against observable reality. As 3I-ATLAS approaches its invisible encounter with Mars, we're participating in the latest iteration of humanity's oldest intellectual tradition, watching the skies, seeking patterns, and trying to understand our place in a universe that regularly presents us with phenomena that challenge our assumptions about what's possible. The question isn't whether we'll find patterns in the data. Pattern seeking is what human minds do automatically. The question is whether we'll find patterns that actually exist, or patterns that we've imposed on phenomena that are genuinely random but psychologically compelling. Let's return to the chemistry that makes 3I-ATLAS so intriguing, a carbon dioxide to water ratio of approximately 8:1, among the highest ever measured in any comet. To understand why this matters, we need to think about Mars, not as it is now, but as it once was, and potentially could be again. 4 billion years ago, Mars possessed a thick atmosphere, flowing rivers, and possibly vast oceans. The red planet's surface bears the unmistakable signatures of water erosion, ancient river valleys, delta formations, and mineral deposits that require liquid water to form. Jezero Crater, where Perseverance is currently searching for biosignatures, represents the remnant of this wetter, more hospitable Mars. What happened to all that water and atmosphere? Mars lost its magnetic field early in its history, leaving the planet vulnerable to solar wind stripping over billions of years. The thin Martian atmosphere we observe today, less than 1% of Earth's surface pressure, represents the residue of what was once a substantial envelope of gases. The current Martian atmosphere is already 95% carbon dioxide, but there's simply not enough of it to create meaningful greenhouse warming or atmospheric pressure. If you could somehow thicken Mars's atmosphere while maintaining its chemical composition, you might begin to reverse the planet's long slide toward frozen sterility. Enter 3I-ATLAS carrying a coma dominated by precisely the gas Mars needs most. The James Webb Space Telescope and Spherix have confirmed the unusual CO2 abundance, along with detections of carbon monoxide, carbonyl sulfide, and water ice. It's essentially a chemistry set designed for atmospheric engineering. Of course, scale matters enormously. A single comet, even one with exotic volatile content, carries nowhere near enough material to meaningfully alter a planetary atmosphere. Mars has been losing gases to space for billions of years. One delivery of cometary carbon dioxide would be like adding a teaspoon of sugar to an empty Olympic swimming pool. But what if 3I-ATLAS represents not a single event, but one component of a larger process? The speculative thought experiment writes itself. If someone wanted to gradually restore Mars's atmosphere over geological timescales, repeated deliveries of carbon dioxide-rich materials would be exactly the right approach. Not enough to terraform the planet quickly, but sufficient to nudge atmospheric evolution in a more habitable direction. The heating patterns of 3I-ATLAS support this speculation in interesting ways. As the comet approaches perihelion in late October, solar heating will maximize outgassing precisely when it's closest to Mars. The geometry creates optimal conditions for atmospheric delivery, if that's indeed what we're observing. Recent spectroscopic data reveals additional complexity in the comet's chemistry. Beyond the dominant carbon dioxide instruments have detected organic compounds that could serve as building blocks for more complex atmospheric chemistry. The presence of carbon monoxide suggests formation conditions very different from the comets native to our solar system. The green glow reported in September adds another layer of intrigue. While the exact molecular processes remain unconfirmed, the coloration could indicate cyanide compounds or dicarbon molecules chemistry that would be highly relevant for atmospheric engineering projects, even if it occurs through purely natural processes. But we need to be careful about imposing design narratives onto natural phenomena. Comets outgas in predictable patterns determined by solar heating and nuclear composition. The fact that 3I-ATLAS releases carbon dioxide when heated doesn't necessarily indicate intentional atmospheric delivery. It could simply reflect the chemistry of its formation environment around a distant star. One proposed explanation for the unusual CO2 dominance involves selective sublimation. If the comet's nucleus is coated with a layer of carbon dioxide ice, this could suppress the release of deeper water ice reservoirs, creating the observed chemical ratios. As 3I-ATLAS continues heating during its approach to perihelion, we might see these ratios evolve, revealing different layers of its frozen history. The timing of maximum outgassing also aligns with 3I-ATLAS's period of invisible proximity to Mars. Earth-based telescopes will be unable to observe the comet during its closest approach to the red planet, creating a perfect window of observational uncertainty during the most chemically active phase of its solar system passage. If this were a science fiction novel, the setup would be obvious: an interstellar delivery system designed to maximize atmospheric contribution while minimizing detection by Earth-based observers. The chemistry is perfect, the timing is perfect, and the geometry creates ideal conditions for both delivery and deniability. Of course, reality operates according to physics rather than narrative convenience. The solar conjunction that hides 3I-ATLAS from Earth is a predictable consequence of orbital mechanics, not evidence of intelligent design. The CO2 outgassing reflects nuclear composition determined by formation processes around a distant star, not atmospheric engineering specifications. Yet the coincidences accumulate with almost satirical precision. An interstellar visitor loaded with greenhouse gases arrives just as we discover potential Martian biosignatures. Its chemistry is dominated by precisely the compounds Mars needs for atmospheric restoration. Its trajectory brings it closest to Mars during a period of maximum solar heating and minimum Earth observation. The European Space Agency's Mars orbiters represent our best hope for resolving these questions. If 3I-ATLAS is indeed delivering significant quantities of carbon dioxide to Mars's vicinity, the Trace Gas Orbiter should be able to detect and analyze the chemical signatures. Mars Express might even image the comet's coma structure during closest approach. What would constitute evidence of intentional atmospheric engineering versus natural cometary outgassing? The signatures would be subtle but potentially detectable, unusually focused gas jets pointing toward Mars' chemical compositions that change based on planetary proximity, or outgassing patterns that don't correlate with solar heating could all suggest artificial guidance. None of these have been observed, but the crucial measurements will occur during the period of Earth's observational blindness. We'll be dependent on Mars-based instruments to tell us what really happens when 3I-ATLAS makes its closest approach to the red planet. The terraforming speculation, while scientifically questionable, serves an important narrative function. It forces us to think about Mars as a dynamic world rather than a static museum. The red planet isn't just a repository of ancient history. It's a potentially habitable world whose atmospheric chemistry could in principle be modified by external inputs. Whether those inputs come from natural interstellar delivery or human engineering projects, the underlying chemistry remains the same. Carbon dioxide, water vapor, and trace organic compounds represent the raw materials for atmospheric restoration regardless of their source. 3I-ATLAS might be showing us what Mars atmospheric engineering could look like, even if it's happening through purely natural processes. The comet carries a chemistry set perfectly suited for greenhouse warming, atmospheric thickening, and organic complexity, exactly what any terraforming project would prioritize. As we approach the October encounter, the question isn't whether 3I-ATLAS will transform Mars. The scale is far too small for dramatic change. The question is whether we'll observe chemistry that teaches us something new about atmospheric engineering, planetary restoration, and the kinds of materials that interstellar space makes available for world-building projects. The real terraforming might be happening in our minds as 3I-ATLAS forces us to imagine Mars not as it is but as it could be. The scientific baseline must be stated clearly. There is currently no evidence that 3I-ATLAS carries living organisms or biological material. Interstellar space is hostile to life as we know it. Cosmic radiation, extreme cold, and vacuum conditions would destroy most biological molecules over the millions of years required for interstellar travel. But the absence of current evidence doesn't preclude interesting speculation about directed panspermia, the hypothesis that life might spread between worlds through deliberate seeding rather than random chance. If an advanced civilization wanted to distribute biological materials across interstellar distances, comets would make excellent delivery vehicles. The chemistry we've detected in 3I-ATLAS carbon dioxide, water, organic compounds represents precisely the molecular foundation necessary for carbon-based life. While these materials could support biology, they don't constitute biology themselves. The distinction is crucial. Having the ingredients for cake doesn't mean you have an actual cake. Still, the timing of 3I-ATLAS's arrival demands consideration. Just as we discover potential biosignatures in ancient Martian rocks, an interstellar visitor approaches carrying the chemical toolkit necessary for atmospheric restoration and biological complexity. The coincidence feels almost purposeful. The popular concept of junk DNA has been largely discredited by modern molecular biology. What were once considered non-coding regions of the genome often contain regulatory sequences, structural elements, and evolutionary artifacts with important biological functions. There's no evidence of dormant cosmic software waiting to be activated by interstellar chemistry, despite the persistent appeal of this idea in science fiction. But the metaphor remains useful for thinking about dormant potential. Mars itself might contain biological switches that could be activated by the right chemical triggers. The discovery of potential biosignatures in Jezero crater suggests that Mars once possessed the conditions necessary for life. What if some remnant of that biological potential remains dormant, waiting for atmospheric conditions to improve enough to support renewed activity? This ventures well into speculative territory, but it's worth considering the mirror effect. The real activation happening right now is human attention and investment. The discovery of possible Martian biosignatures has energized astrobiology research, increased funding for Mars sample return missions, and focused public attention on the possibility of life beyond Earth. In this sense, 3I-ATLAS might be activating human behavior rather than Martian biology. Its unusual chemistry and timing have captured imaginations, generated media coverage, and created a narrative framework that makes Mars seem more alive, more dynamic, more worthy of exploration than it appeared just a few months ago. The panspermia hypothesis, first proposed by Svante Arrhenius in 1906, suggests that life spreads throughout the universe via comets, asteroids, and other celestial bodies. While most scientists consider natural panspermia unlikely, due to the harsh conditions of space travel, directed panspermia intentional seeding by intelligent civilizations remains a theoretical possibility. If 3I-ATLAS were carrying biological materials, what would we expect to detect organic molecules more complex than simple carbon compounds, chemical signatures that suggest metabolic processes, isotopic ratios that differ from non-biological material, possibly even preserved cellular structures that could survive interstellar travel? Current spectroscopic observations have detected organic compounds in 3I-ATLAS's coma, but these appear to be simple carbon-based molecules consistent with natural formation processes. Nothing observed so far suggests biological origin, though the limitations of remote sensing mean we might miss subtler signatures of biological activity. The real test will come if and when we can directly sample material from 3I-ATLAS or similar interstellar visitors. The European Space Agency has confirmed that no intercept mission is possible for this encounter, but future interstellar objects might provide opportunities for direct analysis. Mars sample return currently delayed, but still planned for the early 2030s, will provide our best opportunity to test for ancient Martian biology. The potential biosignatures discovered by Perseverance, those leopard spot textures in Jezero mudstones, could contain preserved cellular structures, organic molecules, or isotopic signatures that would confirm biological origin. If Mars once hosted life, and if that life left dormant genetic material in the planetary geology, then atmospheric restoration could theoretically reactivate some biological processes. This is highly speculative, but not impossible in principle. Earth's subsurface contains dormant microorganisms that can be revived after millions of years of inactivity. The connection between interstellar chemistry and terrestrial biology might be more subtle than direct seeding. Complex organic molecules formed around other stars could provide raw materials for prebiotic chemistry on worlds like Mars. Carbon dioxide, methane, and water, the components we've detected in 3I-ATLAS, are fundamental building blocks for the chemical processes that eventually give rise to life. But we must be careful not to overinterpret suggestive coincidences as evidence of design or purpose. The universe contains vast quantities of organic chemistry. The building blocks of life are distributed throughout interstellar space. The arrival of carbon-rich comets at potentially habitable worlds is probably more common than rare. What makes 3I-ATLAS interesting isn't necessarily that it carries biological materials, but that it's arriving at precisely the moment when we're most sensitized to questions about Mars's biological potential. The comet functions as a kind of cosmic Rorschach test, reflecting our hopes and fears about life in the universe. The narrative appeal of biological connections reveals something important about human psychology. We're pattern-seeking organisms that evolve to detect meaningful relationships in complex environments. When we encounter phenomena like 3I-ATLAS unusual chemistry arriving at meaningful moments, our biological programming activates whether or not genuine biological connections exist. This creates both opportunities and dangers for scientific interpretation. The pattern seeking that helps us detect genuine biological signatures can also lead us to impose biological narratives onto purely chemical or physical phenomena. A reasonable near-term test for biological connections would involve analyzing 3I-ATLAS's spectral signatures for amino acids, nucleotides, or other complex organic molecules that suggest biological processes. Current instrumentation should be capable of detecting such compounds if they exist in sufficient concentrations. The Mars orbiters scheduled to observe 3I-ATLAS during its October encounter could potentially detect biological signatures if the comet were releasing complex organic materials. The trace gas orbiter, specifically designed to analyze atmospheric chemistry, would be our best instrument for such a detection. Whether or not 3I-ATLAS carries biological materials, its arrival has already activated something profound in human consciousness: the recognition that we live in a universe where interstellar chemistry and planetary biology intersect in ways we're only beginning to understand. The question isn't whether 3I-ATLAS will seed Mars with life. The evidence suggests it won't. The question is whether its arrival will seed human minds with the curiosity, funding, and determination necessary to answer deeper questions about life's distribution throughout the cosmos. Are we projecting our origin myths onto a snowball from elsewhere? Or are we finally developing the tools necessary to detect genuine biological connections between worlds? The answer might depend less on what 3I-ATLAS is carrying and more on what we're prepared to look for. Step outside the realm of astronomy for a moment and consider how narratives shape human behavior on scales both intimate and civilizational. The stories we tell about cosmic events don't just reflect our understanding of the universe. They actively modify how we respond to new information, allocate resources, and make decisions about humanity's future. The history of comet interpretation illustrates this narrative feedback loop perfectly. Halley's Comet has appeared roughly every 76 years for millennia, but each appearance generated wildly different human responses depending on the prevailing cultural stories about celestial visitors. Medieval Europeans saw omens of plague and political upheaval. Renaissance astronomers saw a confirmation of natural law and predictable celestial mechanics. Modern observers see opportunities for scientific investigation and space mission planning. Same comet, different stories, different consequences. 3I-ATLAS arrives during an era when our stories about cosmic visitors are undergoing rapid evolution. The successful DART mission in 2022 demonstrated that humanity can deliberately alter the trajectory of celestial objects. We've graduated from passive observers to active participants in solar system dynamics. This technological capability changes how we interpret objects like 3I-ATLAS, transforming them from pure scientific curiosities into potential resources or threats that might require human response. Media algorithms amplify this narrative evolution in unprecedented ways. Social media platforms reward extreme interpretations and emotional engagement over measured analysis. A single post claiming 3I-ATLAS is an alien artifact can reach millions of viewers within hours, while careful scientific papers explaining its natural chemistry remain buried in academic journals with readership in the hundreds. This creates a dangerous feedback loop where sensational interpretations of genuine scientific mysteries crowd out nuanced analysis. The signal-to-noise ratio degrades as speculation multiplies faster than verification, making it increasingly difficult for non-experts to distinguish between legitimate scientific uncertainty and manufactured controversy. The planetary defense infrastructure that detected 3I-ATLAS represents a remarkable achievement in international cooperation and technological capability. The ATLAS telescope network pans stars, and similar systems scan the entire visible sky every few nights, automatically detecting and tracking potentially hazardous objects. This global surveillance network has dramatically reduced the risk of cosmic surprise attacks, but it's also created new categories of public awareness about celestial visitors. We now live in a world where interstellar objects are detected and announced within days of discovery, complete with preliminary orbital calculations, chemical analysis, and risk assessments. This rapid information flow enables unprecedented scientific collaboration, but it also creates opportunities for misinterpretation and premature speculation. The challenge is maintaining scientific rigor while acknowledging that our understanding of interstellar chemistry and visitor frequency is genuinely incomplete. 3I-ATLAS doesn't fit neatly into existing categories of cosmic objects. Its chemistry is unusual, its timing is coincidental, and its behavior during the Mars encounter will occur during a period of limited Earth-based observation. These uncertainties create legitimate space for scientific speculation, but they also provide fertile ground for unfalsifiable claims and conspiracy theories. The key is developing better tools for distinguishing between productive uncertainty, the kind that drives genuine scientific inquiry, and destructive uncertainty that undermines evidence-based decision-making. Educational institutions play a crucial role in this narrative ecosystem. How we teach students to think about cosmic mysteries, evaluate evidence, and tolerate ambiguity will determine whether future generations approach objects like 3I-ATLAS with curiosity or credulity. The goal isn't to eliminate speculation, but to ensure that speculation remains tethered to testable hypotheses and empirical standards. The economic implications of these narratives are also significant. Public support for space exploration, asteroid detection, and Mars exploration depends partly on how compelling we make the stories about why these activities matter. 3I-ATLAS provides an opportunity to demonstrate the practical value of astronomical surveillance, while highlighting the scientific mysteries that make space exploration intellectually exciting. But there's a responsibility that comes with storytelling about scientific mysteries. When we emphasize the dramatic and unusual aspects of objects like 3I-ATLAS, we risk creating expectations that reality might not fulfill. If 3I-ATLAS proves to be a relatively conventional comet with slightly unusual chemistry, will public interest in interstellar visitors decline? Will support for continued astronomical surveillance suffer if the mystery deflates into mundane explanation? The healthy toolkit for evaluating cosmic anomalies should include several key components: source verification, statistical literacy, predictive testing, and comfortable uncertainty tolerance. Claims about 3I or ATLAS should be weighted based on their origins. Peer-reviewed papers carry more authority than social media posts. Institutional statements from NASA or ESA deserve more credence than anonymous internet speculation. Statistical literacy helps distinguish between genuine anomalies and selection effects. 3I-ATLAS is unusual among the 3 confirmed interstellar visitors we've detected, but 3 data points don't constitute a meaningful sample size. As our detection capabilities improve and we discover more interstellar objects, 3I-ATLAS might prove less exceptional than it currently appears. Predictive testing separates meaningful speculation from unfalsifiable claims. Theories about 3I-ATLAS that make specific testable predictions about its behavior during the Mars encounter can be evaluated when new data becomes available. Theories that remain immune to empirical testing, regardless of what we observe, are less scientifically useful. Uncertainty tolerance might be the most important skill for navigating cosmic mysteries. The universe regularly presents us with phenomena that challenge our existing frameworks without necessarily requiring extraordinary explanations. 3I-ATLAS is genuinely puzzling in ways that might not be resolvable with current technology and observational capabilities. The meta-commentary about algorithm-driven information distribution applies directly to how 3I-ATLAS stories spread through digital ecosystems. Platforms that prioritize engagement over accuracy create incentive structures that reward sensational interpretations over careful analysis. Understanding these systemic biases helps us evaluate the relative prominence of different narratives about cosmic events. Visual communication also shapes how we interpret cosmic mysteries. The choice between presenting 3I-ATLAS through sober scientific imagery versus sensational artistic representations influences public perception in subtle but significant ways. Split-screen comparisons between actual spectroscopic data and speculative alien artifact thumbnails reveal how presentation affects interpretation. As we approach the October encounter, these narrative dynamics become increasingly important. 3I-ATLAS will either confirm our natural comet hypothesis, reveal something genuinely anomalous, or most likely provide additional data that refines our understanding without completely resolving the mystery. How we tell that story will influence public support for continued space exploration, international cooperation on planetary defense, and scientific funding for interstellar object research. The narrative stakes are almost as high as the scientific ones. The hidden influence of stories about cosmic visitors extends beyond immediate policy implications. These narratives shape how we conceptualize humanity's place in the universe, our responsibilities as a spacefaring species, and our preparedness for encountering genuinely anomalous phenomena in the future. If 3I-ATLAS is testing anything, it might be testing our collective ability to maintain scientific curiosity while resisting the temptation to impose premature explanations onto incomplete data. The universe is under no obligation to provide us with easy answers or comfortable certainties. What if the most important lesson from 3I-ATLAS isn't about interstellar chemistry or Martian terraforming, but about how human consciousness responds to cosmic ambiguity? What if we're the real subject of this cosmic experiment? Here's a speculative twist that might explain the uncanny timing and chemistry of 3I-ATLAS without invoking extraterrestrial intelligence. What if the aliens responsible for atmospheric engineering projects are actually us? Or rather, an earlier iteration of human civilization that reached technological maturity, then fell, leaving behind automated systems that continue operating across cosmic timescales. This hypothesis requires us to imagine human civilization, or something very much like it, achieving interstellar capability hundreds of thousands or millions of years ago, then suffering some catastrophic collapse that erased most traces of their technological achievement from the geological record. Before their decline, this earlier civilization might have deployed self-replicating atmospheric engineering systems designed to maintain habitability on potentially life-supporting worlds throughout the galaxy. What evidence would we expect to find for such an advanced predecessor civilization? Industrial pollution layers in ancient ice cores or sedimentary rocks, unusual isotopic signatures from large-scale nuclear processes, artificial structures or materials on the moon, where geological processes wouldn't erase them, orbital debris from space-based infrastructure, or genetic modifications in terrestrial life forms that couldn't have occurred through natural selection alone. Remarkably, none of these signatures have been definitively identified, though our ability to detect subtle traces of ancient technology continues to improve. The absence of clear evidence doesn't prove that no previous technological civilization existed, but it does constrain the possible scope and longevity of their activities. But suppose such a civilization did exist and did develop interstellar capability, Mars would have been an obvious target for atmospheric restoration projects. The red planet sits within our solar system's habitable zone, possesses the basic geological ingredients for life support, and once hosted the thick atmosphere and flowing water necessary for biological complexity. An advanced human civilization might have recognized Mars's potential and deployed automated atmospheric engineering systems designed to operate over millions of years. These systems could use interstellar comets as delivery vehicles, programming them with chemical compositions optimized for greenhouse warming and atmospheric thickening. 3I-ATLAS, in this speculative framework, wouldn't be a natural comet with coincidentally useful chemistry. It would be an engineered delivery system carrying precisely the chemical payload Mars needs timed to arrive during the planet's most promising period for biological recovery, the era when a surviving human civilization develops the capability to detect and potentially assist with planetary restoration. The chemistry we've observed supports this speculation in interesting ways. The 8:1 carbon dioxide to water ratio isn't just unusual, it's optimized for Mars' atmospheric conditions. The trace organic compounds could provide chemical complexity for prebiotic processes. The timing of maximum outgassing during Mars proximity suggests targeting rather than coincidence. Of course, this hypothesis faces significant challenges from basic physics and astronomy. Programming interstellar comets to arrive at specific locations as with precise timing would require technology far beyond our current capabilities. The gravitational dynamics of interstellar space make such precise trajectory control extraordinarily difficult even for advanced civilizations. Additionally, we would expect engineered objects to exhibit signatures that distinguish them from natural phenomena, structured radio transmissions, geometric perfection in imaging, non-gravitational accelerations that suggest active propulsion, or chemical compositions that couldn't occur through natural processes. 3I-ATLAS displays none of these characteristics, but the hypothesis deserves consideration because it addresses the central mystery of timing and chemistry without requiring external intelligence. If humans or human-like beings developed atmospheric engineering technology in the distant past, Mars would have been their logical first target within our solar system. The current convergence of Martian biosignature discoveries and interstellar atmospheric delivery might represent the intended coordination of these ancient systems. This framework also explains why 3I-ATLAS appears natural to our current instruments, while exhibiting properties that seem almost too convenient to be coincidental. Advanced atmospheric engineering might be designed to appear natural to avoid detection by developing civilizations that aren't ready for direct contact with their own technological heritage. The motive for such elaborate concealment could be pedagogical, forcing developing civilizations to achieve scientific maturity before revealing the full extent of their technological inheritance. 3I-ATLAS would function as a kind of cosmic examination, testing whether current human civilization has developed sufficient observational capability, analytical rigor, and collaborative capacity to recognize and respond appropriately to atmospheric engineering assistance. The falsifiability of this hypothesis is both its strength and weakness. We could potentially test it by looking for additional engineered signatures that our current instruments might have missed. Narrowband radio emissions, structured light variations, or chemical compositions that evolve in response to Mars's proximity could all indicate artificial guidance rather than natural behavior. The European Space Agency's Mars orbiters provide our best opportunity for detecting such signatures during the October encounter. If 3I-ATLAS is indeed an engineered atmospheric delivery system, its behavior during closest approach to Mars might reveal targeting mechanisms, chemical release patterns, or communication protocols that wouldn't occur in natural comets. But even if we found evidence of engineering, the assumption that human predecessors were responsible remains speculative. Advanced atmospheric restoration technology could have been developed by any number of species that achieved technological maturity before us. The galaxy has had billions of years to produce civilizations capable of interstellar engineering projects. What makes the earlier humans hypothesis psychologically appealing is that it addresses our cosmic loneliness without requiring us to share the universe with truly alien intelligences. If 3I-ATLAS represents advanced technology, we'd prefer that technology to be recognizably human rather than utterly foreign. It's easier to imagine discovering our own forgotten capabilities than encountering genuinely alien engineering. This psychological preference doesn't make the hypothesis more likely to be true, but it does help explain why the idea feels compelling despite limited supporting evidence. We're more comfortable with the notion of advanced humans than advanced aliens, even when the technological requirements are equally extraordinary in both cases. The timeline for such a scenario would need to accommodate both the rise and fall of an advanced civilization and the deployment of interstellar engineering systems that continue operating across cosmic timescales. Earth's geological record suggests that no previous technological civilization achieved industrial capability before the current human emergence, but space-based civilizations might leave fewer planetary traces. Alternatively, the advanced predecessor civilization might have originated on Mars itself during the planet's more habitable early period. If Mars once hosted intelligent life that developed interstellar capability before the planet's atmospheric collapse, they might have deployed long-term restoration systems designed to eventually return their home world to habitability. This Martian origin story would explain why 3I-ATLAS seems so perfectly chemistry matched to Mars's atmospheric needs. It would also explain the timing. Automated systems might be programmed to activate atmospheric delivery when the planet shows signs of renewed biological interest, such as the arrival of spacefaring civilizations capable of assisting with restoration efforts. Of course, we have no evidence that Mars ever hosted intelligent life, and the current understanding of the planet's atmospheric evolution suggests that any complex ecosystem would have had a relatively narrow window for development before conditions became too harsh. But the absence of evidence isn't evidence of absence, particularly for civilizations that might have been primarily space-based rather than planetary. The engineering challenges involved in programming entry. Interstellar comets for precise delivery remain formidable regardless of who might have developed the technology. trajectory corrections across interstellar distances, chemical preservation during millions of years of cosmic travel, and timing mechanisms that activate appropriate delivery sequences all represent technological achievements far beyond our current capabilities. Yet the alternative that 3I-ATLAS's chemistry and timing represent pure coincidence might be even more difficult to accept. The probability of an interstellar visitor arriving with exactly the right atmospheric restoration chemicals at exactly the moment we discover potential Martian biosignatures seems astronomically small. Perhaps the real test isn't whether 3I-ATLAS is engineered, but whether we're prepared to recognize engineering that operates on scales and timelines completely outside our current technological framework. Advanced atmospheric restoration might be so sophisticated that it appears natural to civilizations that haven't yet achieved interstellar capability. The hypothesis of earlier human or human-like atmospheric engineers provides a middle ground between natural coincidence and alien intervention. It allows for genuine mystery and advanced technology while keeping the universe comfortably anthropocentric. Whether this comfort represents wisdom or wishful thinking remains to be determined. As 3I-ATLAS approaches its invisible encounter with Mars, we're forced to confront the possibility that we might be participants in a story much larger and older than we've assumed. The comet might be delivering more than atmospheric chemicals. It might be delivering a message about human potential, cosmic responsibility, and the long-term consequences of technological development. If our predecessors really did deploy interstellar atmospheric engineering systems, then 3I-ATLAS represents both a gift and a challenge. Assistance with planetary restoration, but also a reminder that technological civilizations can rise, fall, and rise again across timescales that dwarf individual human lifespans. The question isn't just what 3I-ATLAS is doing in Mars's orbit, but what we're supposed to learn from watching it happen. Imagine for a moment vast computational networks buried beneath the world's great deserts, quantum processing systems designed to model civilizational collapse, predict optimal intervention timing, and coordinate planetary restoration projects across galactic distances. This is pure science fiction, of course, but it provides a useful framework for thinking about how advanced civilizations might approach the problem of long-term species survival. The speculative concept of quantum archaeology suggests that sufficiently powerful computers could reconstruct historical events from the faint physical traces they leave in quantum fields, subatomic interactions, and information-theoretic residues. While no such technology exists, the underlying principle that the universe retains information about past events in subtle but detectable forms has some basis in theoretical physics. If such capabilities were real, an advanced civilization facing imminent collapse might deploy quantum archaeological systems to predict the optimal timing for species recovery assistance. These buried networks could monitor planetary conditions, track technological development, and activate delivery systems precisely when emerging civilizations reach sufficient maturity to benefit from atmospheric restoration assistance. 3I-ATLAS, in this framework, wouldn't be a randomly timed coincidence. It would represent the output of predictive algorithms that identified the current moment as optimal for Mars' atmospheric engineering support. The comet's arrival coincides with human discovery of Martian biosignatures, development of interplanetary exploration capability, and growing awareness of climate engineering challenges. Of course, this ventures well into speculative fiction territory. We have no evidence of buried supercomputers, quantum archaeological capabilities, or predictive algorithms that operate across cosmic timescales, but the metaphor serves an important function. It helps us think about how genuinely advanced civilizations might approach challenges that operate on scales far beyond individual lifetimes. The reality of modern computational networks isn't entirely dissimilar from this science fiction scenario. The ATLAS telescope system that discovered 3I-ATLAS operates through automated sky surveys that continuously scan for potentially hazardous objects. These networks process enormous data sets, identify anomalous patterns, and alert human operators when something unusual requires attention. The European Space Agency and NASA maintain sophisticated modeling systems that predict asteroid trajectories, assess impact risks, and plan potential deflection missions. The successful DART demonstration proved that human civilization now possesses the computational and technological capacity to deliberately alter celestial mechanics. We've graduated from passive observers to active participants in solar system dynamics, but our current capabilities pale compared to what advanced civilizations might achieve given sufficient time and resources. Interstellar atmospheric engineering would require computational power, predictive accuracy, and technological sophistication orders of magnitude beyond our current achievements. Desert environments provide excellent preservation conditions for both natural artifacts and hypothetical technological systems. The world's great deserts contain meteorites that have remained largely unchanged for millions of years, ancient human settlements that preserve detailed archaeological records, and geological formations that record planetary history with remarkable fidelity. If someone wanted to hide advanced computational infrastructure for millions of years, desert locations would be ideal. Minimal water damage, stable temperatures, low biological activity, and geological isolation would protect buried systems from most forms of environmental degradation. Of course, no such systems have been discovered, and our increasingly sophisticated ground-penetrating radar and geological surveys would likely detect large artificial structures if they existed. But the absence of current detection doesn't entirely preclude the possibility of computational networks designed to remain hidden until appropriate activation conditions are met. The metaphor of desert supercomputers helps us think about the scales of planning that might be required for successful atmospheric restoration projects. Mars lost its atmosphere over billions of years through complex interactions between solar wind, planetary magnetism, and atmospheric chemistry. Reversing this process would require interventions coordinated across similarly vast timescales. Individual comets like 3I-ATLAS couldn't accomplish meaningful atmospheric restoration alone, but they might represent components of much larger, longer-term processes. If atmospheric delivery occurs regularly over millions of years, the cumulative effect could gradually restore Mars to habitability without requiring massive single interventions that would be obvious to developing civilizations. The James Webb Space Telescope represents humanity's current pinnacle of astronomical observation, a quantum leap in our ability to analyze the chemistry of distant objects and detect subtle signatures of unusual behavior. JWST can read the spectral fossils of chemical processes that occurred around other stars millions of years ago, preserved in the molecular signatures of interstellar visitors like 3I-ATLAS. But even our most sophisticated instruments might miss signatures of genuine atmospheric engineering if such engineering were designed to appear natural to civilizations at our current level of technological development. Advanced chemistry might mimic natural processes so perfectly that distinguishing between genuine and engineered delivery systems would require observational capabilities we haven't yet achieved. The fictional framework of predictive collapse modeling serves as a metaphor for real challenges facing human civilization. Climate change, resource depletion, technological disruption, and geopolitical instability all represent potential threats to long-term species survival. Advanced civilizations would presumably develop sophisticated methods for predicting and mitigating such risks. If our hypothetical predecessors really did deploy interstellar atmospheric engineering systems, they might have been responding to their own experience with civilizational collapse. Mars' atmospheric restoration could represent a kind of cosmic insurance policy, ensuring that habitable worlds remain available for species recovery even after planetary or technological disasters. This raises profound questions about our own responsibilities as an emerging spacefaring civilization. Should we be developing similar long-term survival strategies? Should we be planning atmospheric restoration projects for Venus-Mars or potentially habitable exoplanets? Should we be creating backup systems that could assist human recovery after potential future collapses? The DART mission demonstrated that we now possess the basic technological components for celestial engineering. We can detect potentially hazardous objects, calculate precise trajectories, and execute kinetic impact missions that alter orbital mechanics. These same capabilities could theoretically be applied to atmospheric delivery projects, though the scale and complexity would be vastly greater. Testable elements of the desert supercomputer hypothesis would include searchable radio signatures from buried computational networks, unusual electromagnetic anomalies in desert regions that might indicate concealed technology, or chemical signatures in groundwater that could result from advanced technological processes. None of these have been detected, but our search methodologies for hidden archaeological sites continue to improve. LiDAR mapping, satellite-based ground-penetrating radar, and increasingly sophisticated geological analysis might eventually reveal artificial structures that previous surveys missed. The psychological appeal of predictive collapse modeling reflects our own growing awareness of civilizational fragility. Climate change, nuclear weapons, artificial intelligence risks, and asteroid impacts all represent potential threats that could disrupt or destroy human civilization. The idea that someone else has already solved these problems and deployed assistance systems is enormously comforting, but comfort and accuracy are different things. The speculative framework of quantum archaeology and desert supercomputers provides interesting metaphors for thinking about advanced civilizations, but it shouldn't be mistaken for evidence-based analysis of 3I-ATLAS or any other astronomical phenomena. The real archaeological project we're engaged in is much more modest and much more scientific, using increasingly powerful instruments to study the chemistry, timing, and behavior of interstellar visitors, gradually building a database of observations that might eventually reveal patterns invisible to current analysis. 3I-ATLAS might indeed be part of a larger pattern, but that pattern is more likely to involve the natural chemistry of interstellar space than buried supercomputers or predictive algorithms. The universe is under no obligation to provide us with easy answers or comfortable explanations for cosmic coincidences. What if the real test isn't whether we can recognize advanced technology, but whether we can maintain scientific curiosity and rigorous analysis while confronting phenomena that challenge our assumptions about what's possible in the universe? Perhaps the most important question raised by 3I-ATLAS isn't what it is, but how we choose to respond to it. The comet's unusual chemistry and uncanny timing create a perfect test of our intellectual maturity. Do we leap toward comforting explanations that require no effort from us, or do we embrace the harder path of scientific investigation, evidence gathering, and genuine understanding? The test framework isn't necessarily literal. 3I-ATLAS doesn't need to be deliberately designed as an examination for it to function as one. The universe regularly presents us with phenomena that challenge our assumptions, reveal our biases, and force us to choose between rigorous inquiry and wishful thinking. How we respond to such challenges determines our trajectory as a scientific civilization. Consider the real-world examination questions that 3I-ATLAS poses. Can we maintain funding for Mars sample return despite political pressures and budget constraints? Can we keep astronomical survey networks operational and transparent despite their expensive operational costs? Can we resist the temptation to sensationalize genuine mysteries for social media engagement? These aren't abstract philosophical challenges. They're concrete policy decisions that will determine whether human civilization develops the capability to recognize and respond appropriately to genuinely anomalous phenomena. 3I-ATLAS might be testing our commitment to evidence-based decision-making under conditions of uncertainty and public attention. The successful DART mission provides an encouraging model for how evidence-based planetary defense can function. Rather than panicking about asteroid impacts or dismissing the threat, entirely human civilization methodically developed detection capabilities, impact assessment tools, and kinetic deflection technology. When DART successfully altered the trajectory of the asteroid Dimorphos, it demonstrated that careful scientific analysis can lead to effective technological responses to cosmic challenges. This evidence-based approach contrasts sharply with the viral alien artifact speculation that surrounded 3I-ATLAS's discovery. Social media algorithms amplified extraordinary claims, while measured scientific analysis struggled to compete for attention. The signal-to-noise ratio degraded as speculation multiplied faster than verification. NASA's response to the artifact claims illustrates how scientific institutions should handle public speculation about anomalous phenomena. Rather than dismissing concerns outright or engaging in elaborate debunking efforts, space agencies provided clear, factual information about what had been observed and what conclusions were supported by available evidence. They acknowledged uncertainty while maintaining rigorous standards for extraordinary claims. The near-term predictions about 3I-ATLAS's behavior provide concrete opportunities for testing our analytical frameworks. The comet should exhibit evolving carbon dioxide, water, and cyanide ratios as solar heating penetrates deeper into its nucleus during the approach to perihelion. Post-perihelion observations should show characteristic fading patterns consistent with natural comet physics. If 3I-ATLAS were artificially guided rather than naturally governed, we would expect to observe signatures that violate conventional orbital mechanics. Sustained non-gravitational acceleration, beamed radio transmissions, or chemical release patterns that don't correlate with solar heating would all indicate artificial control systems. The absence of such signatures doesn't definitively prove natural origin. Advanced engineering might be sophisticated enough to mimic natural behavior perfectly, but the burden of proof for extraordinary claims requires extraordinary evidence. Without clear violations of natural law, the scientific default assumption remains that 3I-ATLAS represents unusual but natural chemistry following predictable physical principles. The global network of astronomical observatories that track objects like 3I-ATLAS represents one of humanity's greatest achievements in international cooperation and technological capability. The ATLAS system pan-stars, ESA's space-based telescopes, and similar networks provide continuous surveillance of near-Earth space with unprecedented sensitivity and coverage. This surveillance capability means that truly anomalous behavior would be detected quickly and verified independently by multiple observational systems. The transparency of astronomical data publication makes it virtually impossible to suppress or hide evidence of genuinely extraordinary phenomena. If 3I-ATLAS exhibited clear signatures of artificial origin, the evidence would be immediately available to researchers worldwide. The European Space Agency has been exemplary in providing regular updates about 3I-ATLAS observations, orbital calculations, and planned Mars encounter observations. This transparency enables public participation in the scientific process while maintaining professional standards for data analysis and interpretation. Encouraging audience participation in tracking 3I-ATLAS developments represents an important educational opportunity. Citizens can follow official NASA and ESA updates, learn to distinguish between peer-reviewed analysis and speculative interpretation, and develop better intuitions about how scientific consensus emerges from accumulated evidence. The October 3rd Mars flyby and October 29th to 30th perihelion passage provide concrete milestones for evaluating 3I-ATLAS's behavior. These dates represent natural experiments that will either confirm or challenge our understanding of interstellar comet chemistry and orbital mechanics. The choice between transcendence and packaged solutions applies directly to how we interpret these upcoming observations. Transcendence requires that we do the intellectual work of understanding complex chemistry, orbital mechanics, and observational limitations. It demands that we tolerate uncertainty while remaining open to possibilities that might challenge our current frameworks. Packaged solutions, by contrast, offer instant explanations that require no effort from us. Alien artifact theories provide immediate answers to cosmic mysteries without demanding that we learn anything about spectroscopy, hyperbolic orbits, or the challenges of remote chemical analysis. They're intellectually comforting precisely because they eliminate the need for genuine learning. The moral dimension of this choice extends beyond 3I-ATLAS to broader questions about how human civilization responds to cosmic mysteries. Are we developing the intellectual tools necessary to recognize genuinely extraordinary phenomena when we encounter them? Are we maintaining the scientific infrastructure necessary to investigate such phenomena rigorously? Or are we creating information environments that reward sensational speculation over careful analysis, making it increasingly difficult to distinguish between genuine scientific mysteries and manufactured controversies? The stakes of this choice are higher than they might initially appear. As human civilization expands into space, we will inevitably encounter phenomena that challenge our current understanding of physics, chemistry, and biology. Our response to 3I-ATLAS provides a preview of how we might handle truly extraordinary discoveries in the future. If we can maintain scientific curiosity while resisting premature conclusions about 3I-ATLAS, we demonstrate readiness for the bigger mysteries that interstellar exploration will eventually reveal. If we succumb to sensational speculation or comfortable certainties, we reveal vulnerabilities that could compromise our response to genuinely transformative discoveries. The test isn't whether we can solve the mystery of 3I-ATLAS. Some cosmic mysteries might remain unsolvable with current technology and observational capabilities. The test is whether we can maintain intellectual honesty and rigorous methodology while confronting phenomena that resist easy categorization. Transcendence in this context means choosing curiosity over certainty, evidence over speculation, and collaborative investigation over individual opinion. It means funding the telescopes, training the scientists, and maintaining the international cooperation necessary for genuine scientific progress. The packaged solutions will always be available: alien artifacts, ancient astronauts, government conspiracies, or simple dismissal of anything that doesn't fit conventional frameworks. These options require no effort, no learning, and no growth. But the universe seems designed to reward curiosity with discovery, investigation with insight, and patience with understanding. 3I-ATLAS represents an opportunity to demonstrate that human civilization is ready for the genuine mysteries that await us among the stars. The choice is ours, but the consequences will extend far beyond our current understanding of interstellar chemistry and Martian atmospheric restoration. We're choosing the kind of species we want to become as we venture into a cosmos that regularly presents us with phenomena stranger than we currently imagine. October 3, 2025 represents more than just another date in the astronomical calendar. On this day, 3I-ATLAS will make its closest approach to Mars at approximately 30 million kilometers, close enough for the red planet's gravitational field to subtly influence the comet's trajectory far enough to avoid any risk of collision or dramatic interaction. For several crucial hours, an object from the stars will occupy the same region of space that Mars has been traversing for billions of years. Two narratives of cosmic history will intersect: the ancient story of a world that once hosted flowing water and potentially life itself, and the contemporary story of interstellar chemistry arriving from stellar neighborhoods we may never visit. The European Space Agency's Mars orbiters, Mars Express and the Trace Gas Orbiter, represent our best hope for obtaining detailed observations during this encounter. These spacecraft carry instruments specifically designed to analyze atmospheric chemistry, detect trace gases, and image small objects in Mars's vicinity. If 3I-ATLAS exhibits any unusual behavior during its closest approach, these orbiters should be able to detect and document it. What might we observe? The most likely scenario involves standard cometary outgassing enhanced by solar heating. As 3I-ATLAS approaches perihelion later in October, carbon dioxide and water vapor streaming from the nucleus should create a visible coma that evolves predictably based on the comet's distance from the Sun. Any deviation from this expected behavior could indicate artificial guidance or unusual nuclear composition. The green glow reported in September might intensify during the Mars encounter, potentially revealing the exact molecular processes responsible for the coloration. Cyanide compounds, dicarbon molecules, or other trace chemicals could become more prominent as solar heating penetrates deeper into the comet's nucleus. These observations would provide valuable insights into the formation chemistry of interstellar materials. But here's where the two competing narratives diverge most sharply. The gift drop terraforming fantasy suggests that 3I-ATLAS will exhibit targeting behavior during its Mars approach, perhaps releasing concentrated bursts of carbon dioxide preferentially toward the planet, or demonstrating chemical release patterns that suggest artificial control rather than natural sublimation. The natural comet reality predicts that 3I-ATLAS will behave exactly as orbital mechanics and cometary physics suggest, following a precise hyperbolic trajectory determined by gravitational forces, outgassing in patterns that correlate with solar heating, and showing no signs of intelligent guidance or atmospheric delivery targeting. The chemistry that makes this encounter so intriguing, the 8:1 carbon dioxide to water ratio, serves as a perfect metaphor for how we process ambiguous information. Like carbon dioxide thickening an atmosphere, easy explanations can thicken our beliefs until we lose sight of underlying evidence. The question is whether we'll maintain the intellectual equivalent of Mars's thin atmosphere, transparent enough for clear observation, or allow speculation to create dense clouds that obscure genuine understanding. Recent distance calculations place 3I-ATLAS at safe margins throughout its solar system passage. The closest approach to Earth won't occur until mid-December, when the comet will pass at approximately 1.8 astronomical units farther than the Sun itself. These distances eliminate any possibility of direct threat while providing optimal conditions for spectroscopic analysis once the object emerges from solar conjunction. The timing of solar conjunction creates perfect dramatic tension for anyone inclined toward conspiracy thinking. Just as 3I-ATLAS reaches maximum proximity to Mars and maximum solar heating, it disappears behind the Sun from Earth's perspective. For several weeks, our most powerful telescopes will be blind to whatever happens during this crucial period. But astronomical invisibility isn't the same as cosmic secrecy. The laws of physics continue operating whether or not we can observe them directly. Solar heating will continue sublimating volatiles from 3I-ATLAS's nucleus. Gravitational mechanics will continue governing its trajectory. Any unusual behavior during the invisible period should leave detectable traces in the object's chemistry and appearance when Earth-based observation resumes. The European Space Agency has been commendably transparent about the observational challenges and opportunities presented by the Mars encounter. Unlike previous interstellar visitors that pass through the solar system with minimal close approaches to major planets, 3I-ATLAS provides a unique opportunity for comparative analysis of interstellar chemistry in the vicinity of a potentially habitable world. Post-perihelion observations beginning in late November should reveal how solar heating has altered 3I-ATLAS's chemical composition and appearance. Comets typically become more active as they approach the Sun, then gradually fade as they retreat, and their surface volatiles become depleted. Any deviation from this standard pattern could indicate unusual nuclear composition or artificial modification. The Mars sample return mission currently planned for the early 2030s, despite recent delays, represents our best opportunity for directly analyzing the potential biosignatures discovered in Jezero crater. These samples could provide definitive answers about ancient Martian life answers that might contextualize 3I-ATLAS's arrival in entirely new ways. If Mars once hosted life, the chemistry delivered by interstellar visitors like 3I-ATLAS becomes more than academic curiosity. It becomes part of the ongoing story of planetary habitability, atmospheric evolution, and the potential for biological recovery on worlds that have experienced climate catastrophe. But we must resist the temptation to connect these phenomena prematurely. The discovery of ancient biosignatures and the arrival of interstellar atmospheric chemistry might be purely coincidental, meaningful to human observers, but irrelevant to cosmic processes. The universe is under no obligation to provide us with narratively satisfying explanations for astronomical phenomena. The choice at Mars represents more than just competing interpretations of 3I-ATLAS's behavior. It represents a fundamental decision about how human civilization approaches cosmic mysteries, with rigorous scientific methodology or with pattern-seeking speculation that satisfies psychological needs but doesn't necessarily correspond to physical reality. If we choose the scientific path, we'll continue monitoring 3I-ATLAS with appropriate instruments, publishing observational results transparently, and updating our conclusions based on accumulating evidence. We'll acknowledge uncertainty while maintaining standards for extraordinary claims. We'll resist the pressure to provide premature explanations that satisfy immediate curiosity but might obstruct genuine understanding. If we choose the speculative path, we'll impose narratives onto incomplete data, emphasize coincidences over probabilities, and allow wishful thinking to substitute for empirical analysis. We'll find patterns whether or not they actually exist in the data. The pivot point at Mars isn't really about 3I-ATLAS. It's about us. Are we ready to encounter genuinely anomalous phenomena without losing our intellectual balance? Can we maintain scientific curiosity while resisting the psychological comfort of premature conclusions? The Red Planet has been waiting for us to answer these questions for billions of years. In just a few weeks, as an interstellar visitor sweeps past Mars while Earth looks the other way, we'll discover what kind of cosmic citizens we've become. The choice at Mars will echo forward into every future encounter with mysteries that challenge our assumptions about what's possible in an infinite universe. We're not just observing 3I-ATLAS. We're choosing the intellectual framework that will guide humanity's response to all the cosmic anomalies yet to come. In the shadow of Mars, something from the deep past of another sun exhales carbon snow into the vacuum, carrying chemistry that speaks in molecular languages we're only beginning to understand. The hypnotic cadence of cosmic coincidence has brought us to this moment, an interstellar visitor loaded with atmospheric restoration chemicals, arriving precisely as we discover the strongest evidence yet for ancient life on the red planet. What we know with certainty can be stated clearly and without embellishment. 3I-ATLAS originated beyond our solar system, confirmed by its hyperbolic trajectory and excess velocity that will carry it back to interstellar space forever. Its coma exhibits unusual chemistry carbon dioxide to water ratios of approximately 8:1, among the highest ever measured for any comet. It will approach Mars at a safe distance of 30 million kilometers on October 3rd, reach perihelion inside Mars's orbit on October 29th to 30th, and remain invisible to Earth-based telescopes during the most critical phase of its solar system passage. What remains unverified despite compelling speculation must be acknowledged with equal clarity. There is no confirmed evidence that 3I-ATLAS represents artificial engineering, deliberate atmospheric delivery, or any form of intelligence beyond the elegant chemistry of natural processes. The alien artifact theory's DNA activation scenarios and 3,600-year cycles remain unsupported by observational data despite their psychological appeal and narrative convenience. Yet the accumulation of coincidences challenges even rigorous scientific skepticism. The timing that brings interstellar atmospheric chemistry to Mars, just as we discover potential biosignatures in Jezero crater. The chemistry perfectly suited for planetary atmospheric restoration, arriving during humanity's emergence as a spacefaring civilization. The orbital geometry that creates maximum scientific intrigue while minimizing observational certainty. These patterns might be meaningful, or they might reflect our pattern-seeking minds, imposing structure onto random events that seem significant only because we're evolved to detect meaningful relationships in complex environments. The universe regularly presents us with phenomena that appear designed until we understand the natural processes that create them. Here at the crossroads of speculation and evidence, we face a choice that transcends 3I-ATLAS. Do we choose transcendence through patient investigation, collaborative research, and evidence-based understanding? Or do we choose the safety of premature conclusions that comfort our need for certainty but might blind us to genuine discoveries? Transcendence requires intellectual courage. It demands that we fund the telescopes, train the scientists, and maintain the international cooperation necessary for genuine scientific progress. It asks us to tolerate uncertainty while remaining open to possibilities that might challenge our current frameworks. It insists that we do the hard work of learning spectroscopy, orbital mechanics, and atmospheric chemistry rather than accepting packaged explanations that require no effort from us. The transcendent path leads through the European Space Agency updates, NASA observational bulletins, and peer-reviewed papers that will document 3I-ATLAS's behavior during its Mars encounter and post-perihelion evolution. It requires that we distinguish between institutional analysis and social media speculation, that we understand the difference between scientific uncertainty and manufactured controversy. Safety, by contrast, offers immediate relief from cosmic anxiety. Alien artifact theories provide instant explanations that eliminate the need for genuine learning. Ancient astronaut narratives promise that someone else has already solved the problems that challenge human civilization. Government conspiracy claims suggest that all mysteries have answers, they're just being hidden from us. These safe explanations share a common characteristic: they demand nothing from us except belief. We don't need to learn anything new, fund anything expensive, or collaborate with anyone difficult. We can remain exactly as we are while feeling that we understand phenomena that challenge the limits of human knowledge. But the universe seems designed to reward curiosity with discovery, investigation with insight, and patience with understanding. The successful detection and analysis of 3I-ATLAS represents humanity's growing capability to observe and comprehend interstellar phenomena. Every measurement of its chemistry, every calculation of its trajectory, every observation of its behavior adds to our collective understanding of how chemistry and physics operate on cosmic scales. The real revelation might not come from 3I-ATLAS itself, but from the accumulated knowledge that studying it provides. As our detection networks improve and we discover more interstellar visitors, we'll develop better frameworks for understanding the chemistry, frequency, and behavior of objects from other stellar neighborhoods. The Mars Sample Return mission, whenever it eventually occurs, could provide definitive answers about ancient Martian biology that would contextualize 3I-ATLAS's arrival in entirely new ways. If those leopard spot textures in Jezero mudstones prove to be genuine biosignatures, the story of atmospheric chemistry delivery becomes part of a larger narrative about planetary habitability and biological recovery. But even if Mars Sample Return confirms ancient life, and even if additional interstellar visitors exhibit similar atmospheric restoration chemistry, we must resist the temptation to impose teleological explanations as onto natural processes. The universe might be more conducive to life than we currently understand without necessarily being designed for life by intelligence we can recognize. The choice between transcendence and safety isn't abstract philosophy. It has concrete consequences for how human civilization develops over the coming decades and centuries. If we choose rigorous investigation over comfortable speculation, we build the intellectual and technological infrastructure necessary to recognize genuinely extraordinary phenomena when we encounter them. If we choose premature certainty over disciplined uncertainty, we risk creating cognitive frameworks that make us blind to discoveries that don't fit our preconceptions. The universe might regularly present us with phenomena stranger than we currently imagine, and our response to 3I-ATLAS provides a preview of our readiness for truly transformative encounters. As 3I-ATLAS completes its invisible Mars encounter and begins its post-perihelion journey back toward interstellar space, we'll have months of additional observations to refine our understanding of its chemistry and behavior. The data will either confirm our natural comet hypothesis or reveal anomalies that challenge conventional frameworks. Either outcome represents success for the transcendent approach, genuine learning that expands human knowledge, and improves our capability for investigating cosmic mysteries. The safe approach, by contrast, would succeed only if reality conforms to our immediate preferences and expectations, an outcome the universe seems unlikely to guarantee. What is 3I-ATLAS doing in Mars's orbit? Exactly what nature does, following gravitational mechanics, sublimating volatiles based on solar heating, and exhibiting chemistry determined by formation processes around a distant star. Unless we choose to see something more in patterns that might reflect our hopes and fears more than cosmic reality. The final call isn't to 3I-ATLAS but to ourselves. Will we choose the transcendent path of evidence-based curiosity or the safe harbor of explanations that ask nothing from us except belief? Will we build the capability to recognize genuine cosmic anomalies, or will we content ourselves with finding patterns that confirm what we already think we know? In the shadow of Mars, an interstellar visitor continues its ancient journey, carrying chemistry from stellar neighborhoods we may never visit. Whether that chemistry represents natural coincidence, cosmic design, or something beyond our current categories of understanding the universe, waits patiently for us to develop the tools necessary for genuine comprehension. The choice is ours. The consequences will echo forward into every future encounter with mysteries that challenge our assumptions about what's possible in an infinite cosmos that seems equally capable of profound meaning and magnificent indifference to human interpretation. Choose wisely. The stars are watching.